Okay, welcome to Editorial of Codeforces round 880 division 2. So we'll be doing the first question. Okay, so basically what the question says is that there are n number of total robots, and these robots are standing in multiple lines, maybe one, maybe more. And in this line, like they're standing one after another, and each robot claims the number of robots standing in front of it. So in the example given, this robot claims that there are two people standing in front of it. This one claims one, and so on. And we are given the different claims, all of the n claims of all n robots. And we have to judge whether this kind of condition is possible or not. So basically, this is like we'll use frequency array. So the question, see, the value of claim is given to be less than 100. So we'll have a frequency array of size 100. Okay, so here we just take the input, and for now you can ignore temp and max. And we set all elements of the frequency array to be 0. Okay, now what I'm doing is, say, suppose we have this claim 0, 0, 0, 1, 1, and say 2. Now, okay, so 3 zeros means there will be 3 lines, 1, 1, 2, 2. And this is the solution and one of the ways to do it. And in this, you will notice one thing, that if let's assume that all of the robots are telling the truth, like their claims are accurate, then whenever a 2 occurs, then a 1 has to occur, a 0 has to occur. So for any number to occur, all of the numbers less than it should occur. So say there was a 3 somewhere, then for 3 to occur, all 0, 1, 2 must occur. However, if say a 1 occurs here, so let's add another 1, then it does not imply that the numbers after, that is 2, 3, 4, may occur. So basically, if a number k occurs, then all numbers less than k occur in that particular chain, but all numbers greater than k may or may not occur. So sort of this allows us to like come up with a property that the number of ones should be less than or equal to number of zeros. So this is greater than number of ones, and this holds for every element. So every possible element, number of ones should be greater than number of twos, greater than or equal to, okay, me make the correction, and number of occurrences of twos should be greater than equal to number of occurrences of 3. All right, and so basically what I've done is, first I took n as an input, and basically I got temp variable. So in temp variable, I'll be storing the claim of each robot. And in this for loop only, okay, so a lot of stuff is happening in the for loop. So first I take in the claim and I increase the frequency of that claim. If someone's claiming 0, then the frequency of 0 is incremented. If someone claims 1, frequency of 1 is incremented, and so on. And among all these claims, I also find the maximum of the claims. Right, okay. And here what I'm basically doing is, from I equals 1, I less than equal to max, I plus plus. So I'll look at the frequencies of the claims, and the frequency of a larger claim should be less than all of the frequencies that are below it, right? So as I explained, here frequency of 0 should be greater than equal to 1, 1 should be greater than equal to 2, and so on. And what I'm doing here is, I'm using this I to check whether this happens. So if frequency of I minus 1 ends up becoming less than frequency of I, then it's an issue, right? Because for I equals 1, frequency of 1 can't be greater than frequency of 0. So in that case, we'll break. And since I'm running a loop till I equals max, so if I equals max plus 1, means we have successfully run the whole loop, and all of the values, all of the claims are in order. So we'll say yes, and as the answer is no. So I guess, yeah, that's it. Okay, so we'll discuss question B, astrophysicist. So I guess you have gone through the question, so I'll just discuss the important points. So an astrophysicist, total of k gold coins, and these gold coins are divided as silver coins, such that there are a total of k into g silver coins. And this k into g silver coins are assigned to all n people, such that let's assume that each person gets some xi coins, and sum of all xi's for I goes from 1 to n is k into g. Unfortunately, the comparison of financial advice. Okay, so there's this rounding procedure, and we need to look in depth exactly what this rounding procedure does. And our goal is to distribute the coins in such a way such that after this rounding procedure is applied, the final sum is minimum. Basically, we saved as many coins as possible. So, okay, let's take a look at this rounding procedure first. So let's take g equals to 7 for now. And the way this rounding, let's take some like values, say 8, 9, 10, like assume that these are the way distributed silver coins right now. The silver coin bonuses. Okay, so the x originals, and let's look at the remainder because that's what we want, right? R is x mod g. So again, these are 1 to 6, all of the values. Okay, now the way this rounding procedure works is that g by 2, ceiling of g by 2, which in this case is 4. So for all those numbers whose remainder is less than 4, remainder when divided by g. So the first three numbers, these are rounded to x minus r, so 7 for all of these. And the ones whose remainder is greater than or equal to 4, these are rounded to x minus r plus g, so 14 for all of these. Okay, now we basically look at this and sort of understand how this rounding procedure works. Basically, we are rounding off to the closest multiple of g. Yeah, so these three, for these three, 7 is closest, and for these three, 14 is closest. And for an even g, we are rounding off to the higher multiple. We consider it as the closest for g by 2 as a convention. For g equals 8, 4, which is g by 2, it gets upscaled to 8. Okay, so again, so when I mean upscale these three numbers, these are going to the higher multiple of g. So these are getting upscaled in a way, and these three numbers are going to the lower value of g. So these are getting downscaled, is what I mean. Okay, so according to a question, we have to, okay, we minimize the number of coins, the final sum. So we maximize how many coins we lose during this rounding process. So, okay, so what we have to do, basically, we have to maximize the number of downscaling, because in every downscaling, we are losing a certain number of coins, and we minimize the number of upscalings, because in every upscaling, we kind of gain points. So, and even in downscalings, look at this particular example, 10, 7. In this case, we lost 3 coins, which is more than the other two. So this type of condition is the most favorable to us when the remainder becomes just less than ceiling of g by 2. So, okay. So in the general case, we have n people, k into g silver coins, and we distribute this. And again, we distribute this, take the remainder with respect to g and this new distribution, we minimize. Okay, so I'll define some quantity R max, which works such a way that in this case, R max is 3. So basically all values less than or equal to this R max, we will be downscaling. And well, R max, like we can write out the expression like g plus 1 by 2 minus 1, where this by 2 is integer division. And well, how did I, well, you can just like play around with some values, like take g 3, 4, 5, 6, and you kind of see this type of expression. You can just g minus 1 by 2, simplify this. Okay, so we have R max, we have n and kg. Now what we want to do is want to have as many Rmaxes as possible, right? Because here we saw the more the number of threes, the more is the loss. We want to have as many threes as possible. So what I'm claiming is that if we just have n into Rmax greater than or equals to k into g, then we are done. Because now what we can do is we can fill all the n, or some of them we can assign 0, in which case it won't matter, but we can sort of put all kg silver coins to these n people such that no one has more than Rmax coins, right? So suppose like say everyone has like 3 coins. We are continuing the case for g equals 7, and so and say one person has like 2 coins, and all of this in this case get downscaled to 0, right? So n into Rmax is greater than kg, we are done. And what if it's not true? So n into Rmax is less than kg. Okay, and in this, what I'm claiming is that for the first n minus 1, I'll assign Rmax just like I did. So for continuing the case for g equals 7, Rmax is 3. So I'll assign 3 n minus 1 number of times. And for the last one, I'll just keep whatever remains. So whatever, some t or some random integer, some random variable you can assume which remains. And now I'm claiming that this is the most optimal solution. Now, how can I say that? Well, let's say that p, the remaining part, is such that when we divide this by g, the remainder r of p turns out to be less than this floor g by 2. And in that case, well, even this gets downsized. And for the n minus 1, the downsizing is of 3. The downsizing is of R max, which is the maximal downsizing possible. And even this is getting downsized, and we cannot have a downsizing in which everyone has R max, right? For some values of P, this might be R max, but even if it's not R max, it's a downscaling nonetheless. So what I claim is that in this case, we are done. Now, suppose that RP is greater than or equal to g by 2. So in that case, this pth element gets upscaled. And even in that case, I claim we are done, because say we have like all these threes and a p, and this p is getting upscaled. Now we sort of want to change the distribution to make it more optimal. So what we do is we kind of take some elements away from p and we start putting in some of these, right? Because like this is the only way to make it optimal, right? Reduce one of them and like try to see whether it works. And well, say we successfully manage to reduce some elements in p. Like we may just say for certain value of p, say p is equal to 4 or 5 in this case. So we make 2 of these to be 4 and we make p to be 3. We are continuing the case for g equals 7. Okay, so still, if you see this, both of these 4 now get upscaled to 7. And what we did is in an attempt to sort of get this P to downscale, we ended up upscaling one or more of these elements. And this upscaling happens by G because we went from 0 to 7. Whereas P, we managed to downscale it. So it didn't really make a difference, right? We downscaled it by G, and here we may upset the value by G for at least one element. At least one element, it's fine. It doesn't make a difference. But for more than one elements, we have sort of like it's not arrived at the most optimal solution. The original position was more optimal than this. All right. So, and say other ways sort of to change the solution is some of these values get assigned to P. And even in that case, suppose we get 2 and do 3, 3, 3, and P becomes 6. So even this gets upscaled to 7 and this gets downscaled to 0. And we didn't really make any difference because 5 to 7, we are losing out on 2 and gaining 3 here. In this case, we just gain 2 coins and lose out on 1. So the net difference is just the same. It's like, it doesn't matter. So assigning n minus 1 elements as this Rmax value and the last element as whatever remains is the most optimal solution. Okay, see. Okay, so the mathematical part behind this was kind of intense, but the code is sort of trivial. So okay, as I discussed, if n into Rmax is greater than k into g, we just see out k into g because we literally saved all of the coins. Else we'll have this save variable, and this is the remaining part, the part which will directly put in the end. Okay, so the first n minus 1 coins we assign to Rmax, and all of them will get saved, right? Because all of them directly turn into 0. And again, these are the cases which I discussed. If remaining part of G is greater than Rmax, then we just upscale it. So we lose on some of the saved coins, else we downscale it and we gained the respective remainders and then we printed it. So yeah, I guess we're done.
Okay, hi guys. So I'll be giving you the tutorial for C question in Codeforces round 880 division 2. Okay, so yeah, let's get started. I hope you saw the question, and so yeah, this is the question. Uh, I'll just tell you the overview. So basically, we consider equalities of this form a plus b equal to c, and it is given that a has capital A digits, small b has capital B digits, and small c has capital C digits, and these are all positive numbers, and there are no leading zeros. We are requested to find the kth lexicographically smallest equality. Basically, what they want to say is when you list down all the equalities of this form and then you sort these equalities, uh, first based on ascending order of A, then based on ascending order of B, and then based on ascending order of C, we get a list. So in that list, we have to find the kth equality. So basically, that is what we have to do. And I hope it's pretty clear how uh, how we will what do you call sort the equalities at this point. Let's just take a small example to understand. Or yeah, we can just see this. So see, in the first test case, basically, uh, the first number is capital B, the second number is capital B, third number is capital C, uh, first number is capital A, sorry, and the third number is K. So basically, these are the solutions: 1 plus 1 equal to 2, 1 plus 2 equal to 3, and so on. So basically, uh, we are keeping the first number constant and then increasing B, and after we cannot increase it further. We can't increase it after this because if we increase B even more, then C will have 2 digits. So that's basically what you should understand here. And then we go to A equal to 2, and then yeah, so that is what is happening. Let us uh, let us try this problem 15642 and see what is happening. So yeah, how do we get the 42nd equality? So 1, 5, 6. And before that, I just want to say something which should be pretty obvious, but I just want to clear it off. They said we have to output -1 if it is not possible to have k valid equalities at all. Like if they are less than k valid equalities, we should just output -1, and k they gave is greater than equal to 1. So if there are no equalities satisfying the prerequisites, then we can directly output -1. Observe that let's say A is 1, B is 5, and C is some 7. Obviously, if you add these two numbers, let's say this number is 3, this number is 999. Obviously you can't get any number with 7 digits, so it is impossible. But observe that it is possible with 156, because you can have this 9999, you can have some 7, and here you'll get 106. You'll get, get you'll get this. So it is possible with 156. So basically, uh, and also we can have 516 also. This is also possible. Okay, so and this is also possible 155. This is pretty obvious. And this can be 2, this can be 3, this can be 4. It'll be possible. This can be 5 also. It'll be possible. Clearly, it's possible. You can just take some examples and understand. Uh, if this is 4, you obviously can't get a smaller number from the addition of two bigger numbers. So yeah. Uh, so basically, we output -1 when capital C uh, is smaller than the maximum number of capital A and capital B. And also, uh, we output -1 when capital C is bigger than the maximum of A and B plus 1. It can be, C can be the maximum of A and B plus 1, but it cannot be the maximum of A and B plus 2. Okay, so that is what you should understand. Okay, hey guys, so basically let us do it like this. The smallest 5-digit number is 10,000, the largest is 99,999, and similarly for C and A I just wrote it beside. So basically we'll start from smallest 1-digit number to the largest 1-digit number for A. So let us see what the computer, what we want the program to do. So we'll start from A equal to 1. So what is the possible range of B here? That is what we want to find. That is what we want to write a program for. Observe that 1 plus 10,000 does not give a 6-digit number, so the start cannot be 10,000. Okay, start B. And okay, so basically the start of B cannot be 10,000. What can it be? What values of B, like there will be a range of values of B which will satisfy this equality. 10,000 does not satisfy. 9999 does satisfy, and we get 100,000 here. And see that there's only one value of B here. When we have A equal to 2, even 998 satisfies, even this satisfies, right? And even 9999 satisfies. Okay, cool. For 3, 9997 satisfies, and range, here there's a nice range. You can just observe what's happening. For every value of A, we are getting a range of B values which we can have which we can have this equality for. So basically we continue this. Okay, see that for A equal to 1 we have 1, for A equal to 2 we have 2, etc. This is not always going to be the same uh, arithmetic progression pattern. It might not be the same, so we will have to go one by one only. So yeah, we will keep on increasing like that, and we will be counting that this is 1, this is 2, this is 3, and this is 4. So when we reach a total which is greater than 42, we will stop. Okay, I am not sure, 1 second, where this will happen. Yes, this will happen for 9 only. Yes, so basically all for 9 we have 9 and some 9. So basically the total here will, I believe, be equal to 45 by the end. So basically before this the total was I guess 36, and here the total is 45, and we want the 42nd equality. So we can say that the 42nd equality will be somewhere between here, and it is not just somewhere between here, but we can easily find it because we know the starting of B and we know the ending of B. So simply we can say where is total, where is k equal to 42, where k equal to 42. So this is the 37th. We know that we know that, so we have to move. So we have to add 5 from 37 to 42. So basically we'll add 5 from this, we'll get 99996 9. Then we can obviously calculate the value of C also. So yeah, that is how we get it. This is the basic logic for how it works. We basically check the range of B for every A, starting from the smallest value of A until the largest value of A, and we stop when K is between these totals. K is between the current total and the previous total, and then we can just do simple arithmetic to find the value of B, which will have this K value. Okay. Now let us see how to get the starting and final values of B for a certain value of A. Uh, I'll just give you the basic logic. So basically, first we'll see whether 3, uh, whether 3 plus the smallest value possible of B is a valid solution. 3 plus 10,000 is 10,003, which does not have 6 digits, so it's not valid. That is the first statement. That's the first if statement that we will use. Uh, if the current A plus the first possible value of B does have the required amount of digits, then that will be the uh, first value of B in the range over here. But here it's not correct. So how will we get the first value of B? Then we will just observe that uh, 100,000 minus 3 will have 5 digits. So we can use that as starting value. That will be 9997. Okay, so observe that we used two if statements here, and that's how we found the starting value of B. Now we will similarly do it for final also. So now observe that 3 plus the final, see that 3 plus the final possible value of B, which is 99999, that is that does have 6 digits. So that is the last uh, B in the range. So yeah, that is how we are getting the range of B. And in case this sum was not in the range, then we'll have to do something else. Then what will we do? Hmm, start C, end C minus I, end C minus. I'll just give you an example when we will get the second case. So yeah, this is I'm taking a different case now. When we have capital A, capital B, capital C are 155. So when we have A equal to 3, let us find the starting. Let's find the range for small b. So 3 plus 3 plus 10,000, that is having 5 digits. So yes, the starting will be 10,000. Now what is the final thing? Final, we have that uh, 3 plus 99999, that is having 6 digits. So that is not the final, that's not the final B in the range. So how will we get the final B in the range? We will take this, the ending value of C, which is 99999, and subtract 3. So we'll get 99996. So I have showed you how we are getting B in several different cases. I have written it very shabbily over here. Uh, I'll just explain this if you want to understand what I did. So basically, start A, start B, start C, end A, end A, end B, and C. That is all. That is that is this thing. Those are these things. So basically, what I wrote here is, if and here I is ranging from start A to end A. That is basically our A is over here. So for a certain I, how do we find the start? This is okay. This start and finish is the range of B for a certain A. So let us say this I plus start B is greater than or equal to start C, and I plus start B is less than or equal to end C. So basically that means that 10,003 is between the possible range of C. So yeah, so if it is, then the starting range of B is start B only. Else we will find it by just subtracting that the value of A from the end value of C, as we did here. So no, I mean, we did not do it here. We did it in the previous example. Uh, so yeah, and for final also we do similar things. We just do uh, the current value of A plus the final possible value of B with like whatever is possible. If that is in the range between the possible values of C, then we'll say that is the end B range. Here it did not happen. Here 3 plus 99,999, that is having 6 digits. It's not in the possible values of C. So we have to go to the second case, which is we just subtracted A from the final possible values of C, which is here it is 9999. We just subtracted 3 from it, and we got this. So that those are all the cases. So once we get the range of B, we can just calculate how many possible equations we have for that particular A, and we can loop this until we get to the k value that we want. Okay. uh, I think this was pretty confusing uh, tutorial, I guess, but I hope you understood the basic intuition at least. And you can ask some doubt, you can ask the doubts in the comments if you want, and please think about it on your own again, based on the intuition that I gave you. So yeah, thank you.